Hello everyone, this is the fifth video in the series of our discussion on waves and radiation. In this video, we will discuss about the diffraction of waves. So let's get started.
Now let's take the next topic, which is diffraction. Now waves, they have this property of spreading out. Uh, so waves can spread in a rather unusual way when they reach a gap in a barrier or the edge of an object placed in its path. This is called as diffraction, right? So even if you place a object, the waves basically they can you know uh, travel around it, right? So this is kind of like bending of the waves, which is called as diffraction, right? So therefore the bending of waves as they pass through a narrow gap or around an object is called diffraction, right? So this bending of waves as it passes through a narrow gap or any object around the object, that's called your diffraction. So one of the very common example, um, I can't find the name of any place, but you might have seen it in the movies or somewhere where you have a barrier and then uh, next to the sea. So as the sea wave, basically this kind of barrier is used to, you know, uh, break the sea waves and maybe like utilize a larger space for either like a for any kind of construction work if it is close to the sea, just to stop the sea at certain point you build a barrier so the waves they get broken and uh, it helps, right? um, Now as you can see that the waves, the parallel crest, so these waves they are uh, your transverse wave, right? These parallel crest of the water waves become circular, right? Now after crossing the the gap, they get circular, something like this, right? As they spread out on the passing through the gap between the two harbor walls, right? So they get like circular. So these were like parallel waves, but now they get circular. You could see the ripples, they are circular. So that's how, you know, uh, basically in this example, what we are trying to show is the waves, they get bent around the corners. And this bending, it is called your diffraction. Right. Now, diffraction is significant only when the size of the gap or object is a match to the size of the wavelength. So if uh, the size of your object or if the size of the gap, it is almost or like equal to the wavelength, then diffraction is significant. When the size of the gap or the object is much larger, then the wavelength of the waves are only slightly diffracted. So as you can see in this example, if the size of the gap is relatively larger than the wavelength, only a very small portion of the wave is getting diffracted. And as we reduce the gap, or as we decrease the size of the gap, uh, the diffraction it increases. Basically, diffraction is the bending of the wave, right? So now the waves are getting, or they are starting to bend a little more. And in this particular example, as you can see, if we have a very small gap, the waves almost like they are circular in shape. Yeah, so they get circular. They are almost like circles. So as we decrease the size of the gap, or the object is nearly the same as the wavelength of the wave, the diffraction effect is greater. So as we decrease the size of the object or the gap, the diffraction increases, right? So this is like one of the property of your diffraction. Now, another property. So longer wave diffract more than shorter wave. Now, what is a long wave and what is a short wave? So, as you can see over here, that uh, shorter waves, they have higher frequency, whereas long waves, they have low frequency. Now, to give you an analogy, what we can say that the buses traveling on a shorter route generally have higher frequency, right? Because they go from point A to B. If it is, the distance is smaller, they can, you will have higher number of, uh, you know, or not higher number of buses, but the frequency of the buses, they are generally more on a shorter route. Whereas the buses traveling on a longer route, they have low frequency, right? You have to wait a little while, maybe sometimes like half an hour or so, uh, for the next bus, right? Because they have to travel a longer distance. Yeah. So in terms of waves, what we can say, shorter wavelength, they have higher frequency because they travel shorter distance and they repeat very quickly. Whereas longer waves, they have lower frequency because they travel a longer distance, right? So their repetition is, you can say, uh, a bit slower than the shorter waves, right? So what we are trying to say is the longer, let me clear my throat. Uh, where is the, right. So as I was saying, the longer waves, they diffract more than the shorter wave. So if you see, using this example, um, these are the longer waves, right? If it is crossing a hill, they get diffracted more. Whereas the shorter waves, which have uh, lower frequency, they could, you know, they are less susceptible or less affected by diffraction, right? Why diffraction? Again, I'm trying to emphasize on this. It is the bending of your wave, right? So longer wave, they bend more around the object, whereas shorter waves, they bend less around the object. So longer wave are diffracted more than the shorter waves. Okay. Now, diffraction is the property of all waves, right? So whether it is electromagnetic wave or it is mechanical wave, right? All of them, they get diffracted. So some of the examples are your sound wave, ultrasound, and radio waves. lower pitched sounds are generated when something vibrates slower. That is, they will have a lower frequency, right? So lower frequency means they have longer wavelength, right? So in the previous slide, if we see, if the wavelength is short, the frequency is high. So kind of we can say that the frequency and the wavelength, they are inversely proportional to each other. So if you have a high frequency signal, your wavelength will be shorter. And if you have a low frequency signal, your wavelength will be longer, right? So let's write down this relation here. Okay. So sound waves, they can diffract through a door or any or around the buildings, right? And lower pitch sound. So lower pitch sound, that means they will have lower frequency and longer wavelength, right? So these are basically lower pitched sound. They are long waves, right? They tend to uh, travel better than higher pitched sound because around the objects they can get diffracted easily, right? We just studied that longer waves diffract more than shorter wave. So basically they spread out, they diffract through the objects and kind of like spread out, and they are more easier to travel. So this is because low pitch sound have a long wave compared with the width of the gap, so they spread out or diffract more, right? Okay. Now similarly, there is another type of wave, which is your ultrasound. Now ultrasound is a sound with high frequency, right? Um, so it has a very short wavelength, right? So if it has a high frequency, it will be a short wave. Yeah. So they would uh, they will not get diffracted more as in comparison to the sound wave, right? So it is a very short wave compared with most structure in the body even, right? So they will so there is a very little spreading, right? So that is why ultrasound can be used to scan uh, the babies. You go to ultrasound for checking on the babies. So this makes sharp focusing of ultrasound easier, which is good for medical scanning, right? So ultrasound can penetrate into the the human body or through the skin without getting diffracted, and the reflection of the sound is then captured, and then you can kind of get an image uh, of inside what's happening inside the body. So not only for checking the babies, or even if you have any kind of like problem in your stomach or somewhere, so it is a non-invasive method, right? Of getting a picture of what's happening inside any part of your body. So ultrasound is a very common method for medical scanning, right? And it is used because they have higher frequency, that is shorter wavelength, and they will not get diffracted when it is uh, sent to the body. Now, radio waves. So radio wave, it is an electromagnetic wave. Now, longer wave radio signals can diffract around buildings and mountains in comparison to short wave radio signals or VHF radio signal. And now, because of diffraction, long wave radio signals, um, such as your radio 4, which has a wavelength of 198 meters, can sometimes be received in the shadow of hills when the equivalent VHF broadband cannot, right? So again, longer wave, they can diffract more um, than the shorter wave radio signal. So it can be heard on the, let's say, the other side of the mountain because they will get diffracted. So something similar to this example, right? So the longer wave radio signal, they will get diffracted, and even in the shadow of the hill or on the other side of the hill, you can have a good reception. Whereas shorter waves, they will like you won't get a radio signal over here. Um, Now this has been demonstrated quite well in this video, but I would like to just you can watch that video in your free time. So basically, just to show how the radio waves they travel and how the longer wave and the shorter wave they are transmitted. So let's say this is your Earth, although it doesn't look like, but let's assume that this is the Earth surface, and if you have a long wave radio tower over here, right? Um, so as we all know that above the Earth surface, you have ionosphere consisting of ions, right? So the longer wave radio signal, right? So longer wave, they can diffract very easily. So they have, they can be diffracted around the curvature of the Earth as well, right? So they are simply transmitted, and you can have a better reception along the horizon, or even at this side, because they get diffracted quite easily. Whereas uh, in shorter wave radio signal, what happens is they are transmitted through the reflection between the Earth's surface and the ionosphere, right? So this is your ionosphere, and this is your Earth's surface. So the shorter wave radio signal, right? So if you have a short wave radio signal, if you are transmitting, usually they are transmitted to the ionosphere, and they get reflected back, and they travel something like this through the reflection, right? So that's the basic difference between your long wave and the short wave radio signal and how they are transmitted. This is one of the very observable example. If you are next to a building, um, I mean, if your building is next to a busy road or a heavy traffic, you often hear the sound. You know, it's quite disturbing. But if you have a sound shade, what it will do is it will diffract the sound of the vehicles passing by, right? So you can have a peaceful sleep.
So, this is all about the diffraction of waves. If you have any queries, please write it down in the comment section and I'll be happy to answer them for you. In the next video, we will discuss about the electromagnetic waves. Don't forget to like and subscribe to the channel. See you in the next video.